Okay, let's start. Good morning, everybody. Today's lecture in QBI is bimodal experiments, and that is kind of an application of what we have learned. So it's a mix of different things, and also I'm going to go into the topic of some software engineering topics that can be relevant for this kind of experiments. Oh, again, that one. So we have some books again. There is, of course, John Ross. And then in this case, there are a couple of books about data fusion and image fusion. Interesting reading. And some is even going into a very specific topic, is the image registration, which we already talked about last week. And then there are two things that don't show up completely. Let's see if I can convince them. No, I can't. Okay, so one is about unit testing in Python. And the thing that you don't see on this screen is a paper I wrote together with some colleagues in a big software project. And it's a guideline document, more or less, that recommends how to work and behave in different cases when you develop collaborative software. So it's quite a long reading, but if you're interested in the topic, it's actually a good read. And now we are actually on the second but last lecture in this course. And we have gone through a lot of topics, first about how images are produced, how you can handle noise, segmentation and different level of advanced. And then we looked at what can we do with the data afterwards, looking at shapes, structures, also dividing them into different categories. And then with the help of some statistical knowledge, we can even make hypothesis testing on this data. And last week we talked about time series analysis, and today is then bimodal imaging. And what we are going for now is, again, the motivation, why and how, some scientific goals. And bimodal imaging requires that you do some kind of fusion. I haven't said yet what bimodal is. I'll come to that a little bit later. And then we can do some bivariate segmentation. And the second part, I think it will be after the break, is software engineering and repeatability, and how you can promote repeatability by organizing your code in the right way. So we have some imaging experiments and challenges. In this case, I have essentially just taken neutron imaging examples, but it actually applies to many other fields. So we have hydrology in soil and geology. Here is the problem: segmentation accuracy and how to estimate water content in these images. Cultural heritage, in this case, we see a Buddha statue, and with neutron imaging, you can actually see organic material within bronze cast, which you can't do with the X-ray. So this is kind of a showcase for neutron imaging. Here again, we are talking about segmentation accuracy and also about material classification. And material classification, it could be, for example, again with neutron imaging, that you want to look at different types of iron. So you have different classes of iron depending on the phase diagram and crystal changes, and that you can actually see. Then we have building materials, water rising in some porous medium. And again, we have the porous medium example, which is, no, material science example, where we actually look at crystalline structures within the material. And in these cases, we have also problems with penetration power or maybe ambiguous readings. So it's always about improving accuracy is the challenge. And with accuracy, it's not only the values of the gray levels that you want to look at, but it can also be the shape, can also be that you don't know really if is this type A or is it type B, because the contrast is very low. So those are the applications where we can look at different modalities. So if we have different modalities, that would be different, for example, different radiation types, then it could be that the reason for selecting one would be we have a good transmission, perfect. We also have good contrast with this modality. And important is that our relevant features, they are visible, so we can actually detect them. Otherwise, it doesn't make sense to make the images. And that you can also identify different materials in the material. Reason to reject a modality would then be that we have too low transmission. Maybe you even starve out your detector so that nothing coming through. Can also be that you have very low contrast. In medical imaging, for example, you have very difficult to distinguish between different types of tissue. And yeah, for example, between fat and some organs, it's very difficult to find really the differences. Can also be that not all relevant features are visible. So then we actually hide some information if we use the wrong modality. And of course, also ambiguous response, that same thing, different things respond with the same gray value. So that's also a low contrast case. And until now, in all our data, we have only talked about the single modality. If it's X-ray, neutrons, ultrasound, some seismic wave propagation, but it's always one type of modality we have been working with. So now we're going to look into working with several modalities. And the idea is to take the advantage of each modality and bring them together and gain something more in the end. So it could be, we can extend the range of operation, that we can actually detect more features at higher resolution with more precision. Also better spatial and temporal coverage. Of course, we want to reduce the uncertainty in our classifications and really increase the reliability. It could be that the modality that we really want is too noisy. And with the help of a second modality, we could, for example, boost it a bit and tell this is the region you want to look at, and then you start looking at that region. And of course, that also ends up in more robust system performance of the whole analysis. In an imaging experiment, we have different players. So one thing is, mostly when you want to do an experiment, you have an application. And with this application, you have to somehow do a measurement, which is based on the physics, some interaction between the objects. And then when you have let the physics play, you can create some images which you acquire and bring into the computer. And finally, you have also to analyze the data. And the interesting thing here now is that if you remove one of these balls, the whole pyramid will fall apart and you can't finalize your experiment. And here is a collection of different modalities or modality combinations that we are talking about. This is the combination X-rays and neutrons, which I'm working a lot with. And you can see here, I have tried to paint the periodic table with the attenuation coefficient for each material. And you can see for X-rays that it is essentially increasing with the density of the material. With neutrons, it's a quite wild thing. You can see, for example, our lightest element has high contrast. And if you look down here somewhere, you can find lead, which is pretty bright. So we can actually see through some centimeters of lead and still see some organic material. And the combination then can actually bring us more information about the main application I'm studying is porous media and geology. And the X-rays would then provide more information about the geometry of the sample. And the neutrons would tell us about where the water is distributed within the sample. Or hydrogen, there can be hydrogen bound to something. In medical imaging, there are also a collection of different modalities that are combined. So we have MRI and X-ray CT. And in this table, you have different modalities. So here MRI and X-ray. And then they have fused it so they can get information from the MRI with the nice structures provided by the X-rays. That can be further also. So you have MRI combined with PET, and then you can fuse those two. And finally, you have also MRI combined with SPECT and can fuse those images. So it's some of these methods, they are very low resolving, but you still want to know a little bit more about the position where they are. And the fusion can then give you a nice feedback when you combine them. Another application is creating infometry. Is actually different measurement technique using a single radiation type, could be X-rays or neutrons. And what this technique is that you put gratings in the beam. And with that, you can extract differential phase contrast and also dark field contrast, which is additional information to what you normally see in transmission imaging. And these can, of course, also be fused together into single images to extract more information. This is not really an example of multimodality, but it's anyway many images that you have to combine. And that would be a spectroscopic imaging, where you do a spectrum of different wavelengths in the material. And here is an example of polycrystalline iron compared to single crystal iron. And with that added information from the spectrum, you can extract more information. Then we have different other modalities and their dimensionality. So it could be that you have on one side 3- or 4-dimensional data, but you want to combine it, for example, with a temperature sensor. Then you only have single dot measurements, but still it's a kind of fusion you can do with the data. You could also have only surface information if you do a surface scan of an object. And then you can also, in some cases, work with single radiographs versus tomography data. For example, if you have a time series, you may not be able to do a tomography because it takes too long time. And then the typical workflow is that you do a tomography in the beginning and a tomography in the end when you have steady state. And in between, you do only a radiography time series, and then you can do mapping between the two of them. So with this, you can include information about temperature, flow rate, and pressure in the data. And now that we have different ways of acquire information, now we want to fuse them also. And that's the kind of mixing, you can say. So it's the data fusion or image fusion is how you can combine sensor data in a common representation. So you can see the information from both and enhance it in a single view. And the aim of this is, of course, you want to improve quality of the information. And ideally, it should also be, you have more gain than if you only used one single modality. Otherwise, you have wasted your resources. There are different approaches to how to do this fusion. And in the beginning, when I started working with this, there was always, yeah, do you have the solution how to do it? No, there are different ways. So depending on what you want to achieve, you have to select a different path in the fusion. So one way is the full package thing, is multivariate fusion. So you really use images or voxels on the same way and combine them in some kind of, say, statistical framework to gain more information. You can also talk about augmented fusion. And in that case, you do something with one modality and something else with the other modality. So it could be that you use one modality to extract structures, to tell modality 2, look in those regions. Because the regions in the second modality, they may be diffuse. You saw, for example, the SPECT images from medical imaging. It's not very easy to see where you have the structures, but if you have modality 1, which was MRI in that case, that one can really tell you where are the things to work with. And then you can use it also for artifact reduction, that with the help of the second modality, you can exclude that this point, it can't be that high value or low value. And then with the help of that, you can tell, okay, this is the place to fix something. Of course, you can match everything in a single combination of everything. That is also possible, because it may not be sufficient to only use, for example, multivariate fusion, because it doesn't give you all the answers. Maybe you have to do some augmentation fusion too. And how you choose it depends also, again, on the experiment type you do. So the sample composition, what are actually your questions? What is it you want to know from the data? And finally, also the condition of the data. In some cases, you may have to do artifact reduction or some smart filtering based on the different modalities. In other cases, you don't have to. So the choices, they vary from experiment to experiment and from task to task. And then there are different levels of fusion. These are very abstract descriptions, but you can say that you have fusion data to data. That would be, you combine two images and you get another image. Then you have data to feature. Then you use the two in order to extract some features, could be structures in the data. Even higher level, then you have already extracted features from the two modalities, and then you try to start combining those features together. And on the higher level, then we even have features to decision. So you already have features extracted from the images, and from those features, you want to combine them and make a decision. Am I good? Am I bad? Or something like that. And well, really abstract, and we go decision to decision, then you have already made a lot of decisions. So that would be something in the type of, if you remember the decision trees and forests, that would be something we would be talking about in that case. The workflow for image fusion is that you have some data. The data is typically images from two modalities, may even have different shapes. Of course, you need to do some registration because you are most certainly not having the same pixel size or resolution in the data. And it's very likely they are not even rotated and oriented in the same way. So that is for sure the first step that we need to do. Then we go on to pixel fusion, where we fuse pixel to pixel. And once that is done, we can go on to feature fusion. And there you can see that you have identified different features here. The mouth here is green and the one is blue. And you want to make some combination out of those. And the final is the decision fusion, where we try to match up decisions and labels in the data. And in the end, depending on where you stop with your fusion, you go on to the, you get the result, which you can use then to create some statistics, model data, or you want to do some presentation with it, visualization also. And then there's a term called catastrophic fusion. And that means you take a lot of stuff, put it together, think I'm great. But in the end, you're actually more misleading, and that can result in a combination that even performs worse than you did on a single modality. So the message here is don't fuse because you can, because that can lead to bad results, or you will at least lose a lot of time on it. Reasons for it is that you have selected the wrong variables in your fusion, or it could be even that you have a too complex combination. There is not enough information that would correlate into a good result. And if you're unfortunate, it can even be that sensor information is canceling each other out. So you get worse result because of one is pointing in that direction and the other in that direction. And in the end, you have nothing in the middle. Image registration is something we did already last week, but I just want to revisit it. And in principle, what you have is two images. In the time series case, we had the same type of images, but now with different modalities, we have images with different contrasts. So you have one fixed image and one moving image. And the idea is that you should flip it and move it in the right way, and in the end also scale them in a way that you can match them on top of each other. So that is what you can see here. First, I did some moving, then I needed to rotate. And finally, I also scaled and cropped it a bit. And then you can see that they are more or less overlapping these images. So this is a soil column where later water was also going into the sample. When you're doing the registration, you have to think about how to do it. The registration problem, depending on what you're doing, is a problem with very many local minima, and that you could also see last week, that this bone structure sample, there were so many structures that was quite similar, and it actually got stuck in a local minimum and never reached the right point. So then is the question if you want to do manual or guided registration. So with the manual, you do everything yourself with visual feedback. You can also guide the registration by providing landmarks or fiducial points in the data and tell this point and that point, they actually are the same. And then the registration has that as a guide for the process. And you can, of course, also provide a course pre-registration, which helps a lot to avoid the local minima. And if you look at this data, it's a lot of repeated structures. They look almost the same. And therefore, it's often very useful to be more or less on the right scale, more or less on the right rotation. before you start the automatic optimization. And the automatic registration is first an iterative process where you iterate and move more and more, and to get the right place, you have, as you saw last week, different metrics to work with. And a problem when you have multimodality is that you may lose some common landmarks. Going back on this one, you can see that, for example, up here, there is completely dark, whereas here you have very bright spots. So they cannot be used as a common landmark. And this is the point where actually the insertion in the experiment already with fiducial points are usually in irrelevant regions introduce small copper balls that can be used for the registration. That helps quite a lot to have those. And here is an example of qualitative fusion. So we have here done registration and co-visualization. And this is a saw that was found in Lake Zug. And the archaeologists, they came to us and wanted to make a replicate. And the problem was the combination of materials in this sword. You have steel, you have wood, you have amalgam, and there was something else, which I don't remember. But anyway, the amalgam was horrible for the X-rays because it contains mercury, and that it just gave horrible streaks. With the neutrons, it was, on the other hand, quite transparent, so we could nicely see the wood that we couldn't do with the X-rays because of all these streaks that were introduced by the amalgam. And the result afterwards was a nice movie. I think it's even on YouTube somewhere. And then they took it to the exhibition, and they even made a replicate completely as it was for the display afterwards. So now let's play with some real data. Here we have two examples. We have X-ray and neutron data from what is it called? The house of a snail. And you can see that there are different informations in the two of them. And here I just did some color code mixing of the two. And one thing when we do this registration is that you, at least in the beginning, you need to have some visual feedback. How well did I do? And one technique is to use a checkerboard. And here I provide you a little bit code to produce this checkerboard. And the idea with it is that you can mix the images, so you can display the two images together, where you have alternated modality 1 and modality 2. So it's quite helpful for the check if you did the right thing with this registration. Can of course also play with different color codes to get better contrast between them. That's up to you how you mix it. Another way is to use color channel mixing. So then you take one, we work with the RGB images, and you take one color channel for modality A, one color channel for modality 2, or B, yeah. And the last one, you take the average intensity between them, and that gives also an intensity. And with that, you can see that you have different responses. Here you have red, green. Here you have blue and green, and this is red and blue together. And you can see that there are different codes. Some look more toxic than others. And the choice is what you think makes sense for your visualization. Sometimes it's actually quite good also in presentations and publications to show this kind of mixing. Even though they're just qualitative, it gives a good overview of where you have the information and what's happening and where. The last combination I'm using very much for the combination of water and some porous material, because the water comes out nicely blue and the other material comes out brown, which is kind of a soil color. So it's that one I like a lot. The typical go-to mix is actually that one, because it's natural. R comes first, G comes second. Let's do it that way. But you can use actually different combinations pretty well. And this little piece of code here, you have image A and image B, and then you can say the order in which how the mixing should be done. So that order can be permuted, and then you can get these different color combinations. Segmenting with the bimodal data is, of course, a task that we cannot avoid so easily. We usually want to segment our data to make our conclusions. And if you do imaging with a single modality, then you have the distributions of the two items that you want to look at. And you see here in this case, they are very heavily overlapping, and you have a lot of misclassifications unless you have a smart segmentation algorithm. And if you look at two modalities, each one of them actually behave more or less the same. And now you can see, however, that in one case, the blue histogram is to the left, and here it's to the right. So they have actually flipped, but the effect in the histogram is the same, and it's hard to tell what you actually have. Now, if you then look at the bivariate histogram, then you can nicely separate these two, because they are different classes and they just are placed in different places of the bivariate histogram. And this histogram is when you take the same point in the two images and plot them somewhere in the 2D form for the histogram counting. And this one is quite easy to segment, to be honest. And here we have an example of these two. We have roots in soil, where you can see in one case, you can nicely see the roots, and in the other case, you can see some stones. Also, the container comes out more or less visible. And this produced bivariate histogram that looks like this. And looking at the details in this histogram, I can tell you that this one is the background. This is the main mass of soil and the soil material. And these two here, this is the container and that are the roots. So you can really identify different features easily, which you couldn't so easily segment or identify if you look at the histograms of these two. Here, by the way, I've used a logarithmic scale for the visualization. And the segmentation can be done using images from the different modalities that, of course, are registered, also artifact corrected. That's actually a thing that is very important. If you go back to this one, you can see in particular in this case, in the X-ray data, there is a heavy cupping effect. And cupping is something that comes from the beam hardening, that at the perimeter, you have brighter pixels than in the middle. And that gives you a profile that looks like a cup. And for segmentation, this is not so easy to work with. It's usually also very visible in the neutron images, in particular when you have a lot of water in them. But then it's not beam hardening, but it's scattered neutrons actually, which are the dominant role for this cupping. But that is a quite annoying thing when you do the segmentation. And then the idea is that we want to do some segmentation here. You have different hypotheses. You have hypothesis 1 is maybe the background, 2 is the soil, and so on. And then for each of them, you have a probability distribution with some center value and a covariance matrix. And then depending on the method you choose, if it's some clustering technique, if it's statistical analysis, that's up to you. But in principle, this is what we want to identify in the image. And here are some ideas that we can work with that we have already passed through. I think was it lecture 5 or 6, where we have k-means, k-nearest neighbors, regression techniques or neural networks. So these are techniques that we could use for this analysis. And another one, which I haven't shown until now, is the Gaussian mixture model. And here we talk about the shape of these distributions is more or less Gaussian most often. There are cases when they are not Gaussian at all, and then this is not a technique, of course. But in principle, what we have is a sum of several Gaussians with different amplitudes. And let's see if I can show this. No, it's not. There is no space for it. Okay, then I'll, oops. So here I have some data, and you can see more or less that there are two typical parts here. And this is our play data. Now I somehow got, unfortunately, I got a version clash or something. So this little example here doesn't show up. I will fix it before I upload the final version of today's lecture. But what you would see here is how the Gaussian mixture is identifying as many Gaussians as you ask for. So if you set a single Gaussian, of course, it will produce a Gaussian that is fitted across a little bit, 45 degrees rotated and fitted on the top of all data. If you have two, then of course you will have one going slightly diagonal, pointing to upward toward right, and another one which is pointing downward towards the right. And if you then increase the number of Gaussians, then you will have more and more blobs that are overlapping. I think it fits first one blob here, and then if you take 3, it fits 1 here and 1 here. And if you take 4, it takes 2 blobs on that one and 2 blobs on that one. So it will provide different, so many fittings as you ask for. So it's similar to k-means in that sense, that you get what you ask for. And now I just want to switch back to the slides. So, oh, that didn't fit in at all. No, then I need to show it like this in that case. Yeah, anyway, here it is. We have different ways. Once we have identified these Gaussians, we can do classification based on distance between the categories. And actually, I think I can do it like this instead. Yes, I can. So good. So the easiest is to compute Euclidean distance. Then you just work with averages. So you have the center of class 1, distance to center of class 2. That one doesn't take the shape of the Gaussian into account. So The next way of work to find the distance is to use the Mahalanobis distance, which, as you can see now, not only has the values of the averages, but also the covariance matrix. And that gives you a better precision and the ability to separate different classes better. The last one is also, it's even more complicated, including the covariance matrix of the different classes. Here is the average covariance matrix, and it gives you an even more precise distance between two classes, or between a value and two classes. And here you can see visualized what it means. If you have the covariance, if you have the Euclidean distance, then you more or less just look at a point somewhere in the data, and you just compute the Euclidean distance to them. In the Mahalanobis distance, then you have the point, and you see actually if it is covered by the covariance region of each Gaussian. And in the last one, you even have a covariance of the point you measure, and that gives you a better overlap between the classes. This one, these two only require a single point, but the last one, then you have to also compute the covariance information locally for each pixel. So then you have to actually compute more information in order to get your conclusion. And here I did some segmentation on the root data with Euclidean distance. And I have got the classes here, as you can see. And the Euclidean distance gives me these areas which would be dedicated to different classes. Now, if you look at this image a bit critically, and then you see that here the roots are coming out quite well, but it actually says that you have some of the container material in the roots, which is not true. And also out here, the roots on the container wall, they actually turned out to be container. The reason for this is actually the cupping that we have in our data, and that makes this decision a little bit harder to do. There is also the thing that I showed about multi-class segmentation, that you have soil outside of the container, which is also not true. And that is when it goes from one class over one or two more classes in order to reach the outside class. So this is not a final segmentation, but it's at least an indication of how it can be. Then, oh, that one I need to do a lot smaller. So we can also play with the Beer-Lambert's law because you have attenuation coefficients. And this includes material density, atomic weight, microscopic cross-section. And with that, we could, in principle, put up an equation system to solve. But this is more a hypothesis of what you could do. I haven't seen it working, honestly, yet in reality. But it's an idea that we want to pursue in the future. And the last thing is beyond multimodal, is that we not only do the multimodal experiment, but actually combine multimodal with dynamic, and then we need special setups that makes it possible to acquire both data at the same time in order to follow up with both. What happened here? So okay, to follow what happens with both modalities at the same time, as long while the process is moving. And that brings us to break.